So at this point, we want to talk about how to actually find the roots of polynomials that won't factor. First thing you want to do is use the rational root theorem to generate a list of possible rational roots. Then you want to use the table on your calculator to find one root. So you're looking for one that when you substitute in, it will give you a y value of 0. Then you want to perform synthetic division on that root. Now let's stop for a minute and talk about that step. A lot of teachers will not allow you to utilize that option. A lot of instructors want you to go through and try synthetic division on the numbers in that list until you find one where the remainder is 0. I will let you use the table on your calculator and I will show you how to do that, because personally I don't think synthetic division is the issue here. I think solving is the issue, and I think it's more important that we're able to work more problems more quickly than to spend most of our time checking 7 or 8 different possibilities using synthetic division. So you need to be sure though that if you have an instructor other than me, that you are allowed to use that table on your calculator. If not, you'll have to test them all using synthetic division and look for a remainder of 0. Okay, so once you find one solution, you need to rewrite your equation in factored form and continue to solve the remaining parentheses equal to 0. You should get as many roots as your highest power unless some have multiplicity. Now I'm going to caution you here. I will allow you to use the table on your calculator to find the first rational root. But you must show your work beyond that so that I know you're comfortable actually showing your work and you're not just plugging in numbers, guessing, and checking. In the event that you wind up with an instructor at a later level who does not allow the use of a calculator at all. And we've talked about this. Several of the colleges are going back to no calculators for college algebra and Cal 1 and 2. Okay, so let's kind of get started and just see what an example of this might look like. We're going to look at the example which asks us to find the roots of the polynomial 2x cubed plus 3x squared minus 8x plus 3. Now the first thing we want to realize is that if we're finding the roots, that's the same thing as asking us to solve it equal to 0. So that's the very first thing I'm going to do, is I'm going to rewrite it equal to 0. So we have 2x cubed plus 3x squared minus 8x plus 3 equals 0. Then I'm going to use the rational root theorem to generate a possible list of roots. So our possible rational roots are plus or minus the factors of the constant. So in this case, the factors of positive 3, which would be either 1 and 3 or negative 1 and negative 3. So we'll list the 1 and the 3. And then the factors of our leading coefficient, which are just 1 and 2. And now if I split that up, I get 1 over 1 and 3 over 1. So I have plus or minus 1 and 3. And then I have plus or minus 1/2 and 3/2. Okay, so those are all of the possibilities. And I need to figure out one of those numbers that will make this equation equal to 0. So I could just start doing synthetic division on each of those. Positive 1, negative 1, positive 3, negative 3, positive 1/2, negative 1/2, positive 3/2, negative 3/2, until I come to one that would give me a remainder of 0. But for the sake of time, we're going to go to our calculator and we are going to type in the equation into y equals 2x cubed plus 3x squared minus 8x plus 3. So we're going to go use that table function on our calculator to look at this. So let's pause for a minute and everybody get ready with their calculators. So let's prepare our calculator for this. First off, we want to make sure that we're in what we call Ask Auto mode. So we're going to go to Second Window, and we want our calculator to allow us to input the x value. So it's going to ask us for the x values and automatically give us the y value. So that's the first thing we want to do, is set up the calculator to be most user-friendly to the process we're trying to do here. Then we're going to go to y equals, and we're going to type in our equation. 2x to the third plus 3x squared minus 8x plus 3. And you want to make sure you have everything typed in properly. Once we're sure that we have everything typed in properly, we're going to go to the table, which is the second graph button. Right now my table is empty, so I want to put some values in there. And we know the values I want to test are positive and negative 1, positive and negative 3, positive and negative 1/2, and positive and negative 3/2. Now you only have to test them until you get a y value of 0. So let's try the ones first. Those are always the easier ones. So let's see. Positive 1. And look at that. Right off the bat, we find one that equals 0. If we hadn't, we'd moved on to negative 1, and then 3, and negative 3. And most people prefer to save the fractions until the very end. Most people would rather not do synthetic division on fractions if it's avoidable. So always try your integers first and try your fractions later. So we see that positive 1 works. So let's go through right now and let's try synthetic division on positive 1. So here we have positive 1, and then we take our coefficients in order: 2, positive 3, negative 8, positive 3. We'll perform synthetic division. And sure enough, we get a remainder of 0. And remember, you have to get a remainder of 0 or that synthetic divisor is not a solution. So we know right now one of the 3 possible answers to this equation. We know one of them is 1. So the question is, where do we go from here? Well, from here you write it in factored form, which means that if positive 1 works, then x minus 1 is a factor, and that leaves us with 2, and the original power was a 3, so we drop down to 2x squared plus 5x minus 3. And we set that equal to 0. Now at this point, we're already down to quadratic form for this problem. If we weren't already down to quadratic form, we would actually have to start the process over. You can't solve by hand until you reach quadratic form. So your highest power has to be quadratic. If we're not yet, if we were still at the 3rd power or the 4th power, what we would do is we would go back and we could start back over and find another solution by performing, looking at the possible rational roots and starting over. But this time, we would check this into our calculator, into y equals. Because now we would be looking for one that would make this equation true. But the nice thing is you don't have to redo the rational root theorem. The same list from before would work. And believe it or not, you can also check 1 again because it could be a double root. So we'll talk about that a little later on. We'll do some higher level. Let's see about finishing this one up for now though. Because we've already dropped down to quadratic form, I can take that equation and I can see whether that parenthesis that contains the quadratic will factor further. If it won't factor further, I'll have to use the quadratic formula on it. Let's see if it will factor. It's a trinomial, so if it factors, it will factor into 2x and 1x, and then 3 and 1. So the outer would be 6x and the inner term would be positive 1x, and sure enough, if I let this be positive and this be negative, it factors out perfectly. I know some of you guys use bottoms up, and that's fine as well. Do whatever it takes to get it either factored or solved. If you want to, you can go straight for the quadratic formula. It's really entirely up to you. Then we solve each factor equal to 0. X equals positive 1, x equals positive 1/2, and x equals negative 3. Those are the 3 solutions that will make that polynomial equal to 0. They also happen to be their x-intercepts. Because none of them were imaginary, they all will show up on a graph as crossing the x-axis. Remember that they could be called zeros, solutions, or roots. And it turned out in our case that all 3 of them were rational. So they all came from our list of possible rational roots. Sometimes You'll get radicals, or you will get complex numbers, which contain imaginaries. And so some of those roots wouldn't show up in your list of possible rational roots. But in this case, they did. So we could certainly go and check each one of those into the table on our calculator, just to be certain we hadn't made any mistakes.